So this is Carl Hibbitts, and he will talk on the sequestering and spectral nature of cometary CO2 and water on warm airless bodies. And there you go.
And I really want to appreciate or say thank you to the last speaker for a wonderful introduction. There was a line in one of his slides that said, the interaction of water molecules and space weather at silicate surfaces are poorly understood. And this is a topic that we've been exploring, especially with the help or led by Tom Orlando and Michael Poston. Michael will be speaking later in this session, so hopefully you'll stick around for looking at the results he will be presenting. And Darby Dyer and Greg Greaves. Greg's doing some modeling work, and Darby is the lunar mineralogist that keeps us all honest. So I want to talk about water versus OH, because the differences are important, and origin stability and thermal evolution. Just touch upon these in a few minutes. And in my lab here at APL, we're looking at the spectral stabilities and qualitatively, the spectral nature, and qualitatively the thermal stability for water, OH, and CO2 on different materials. The premise of this talk is that the physical interaction of water and OH, or any volatiles with a refractory material, can be important in that the interaction can induce a thermal stability greater than you see for ice, and thus you can have potential reservoirs of volatiles at temperatures greater than that at which ice would be stable. And this may not be a surface phenomenon, but could be a near-surface phenomenon as well, and has implications for ISRU. It's something of great interest to several of us here. Anyway, OH water, CO2, just a standard slide that shows, yes, solar wind can produce OH. Comets and wet asteroids deliver both water and CO2, and of course you have internal water on the moon, and on icy satellites we think there are at least there's some thought that the CO2 detected there can be internal as well. All right. So solar wind forming OH but H2O. This is a question that's still open, and even in this room we debate about whether you can form H2O or not from solar wind. But the premise is that solar wind comes in, and the proton goes into the surface tens of nanometers in, and it bonds with a or sees a local oxygen, and you see that spectrally as an OH feature. The question that we're trying to grapple with, and Greg, I think, is leading that model, perhaps Michael now, is what happens when this hydrogen migrates out? How quick can that happen? And when it leaves, does it leave as H2 or H2O? Most likely it doesn't leave as OH. But it's not a trivial question. It's not a certainty that you can produce H2O by any means by having accumulation of hydrogen inside the surface. I think the spacecraft impact data shows that when you bombard an illuminated surface, you do release a lot of hydrogen, and that's to be expected, but maybe not H2O. Okay. However, if you do have a pre-existing source of H2O, such as, I'm getting ahead of myself, the surface grains, this is just to show a real picture of what I just showed before, which is that on the right, you have a rim that's been basically saturated with hydrogen. It alters the upper surface, upper 100 nanometers, and given enough time, you can reach saturation. And at that point, perhaps you can start producing OH or losing the hydrogen as H2. Okay. But the question of interest then, let's say you have a pre-existing source of H2O, not just solar wind, a cometary impact, for instance, or internal source. Does all this get lost at 110 Kelvin over time? Does it stick around longer? And Michael's going to go into much more detail. But some work on analog materials that was done at Georgia Tech, work by which I mean these materials in powder or I should say slab form are maintained in an ultra-high vacuum at 10 to minus 10 torrs, heated up to 750 Kelvin to desorb any terrestrially adsorbed OH, and then dosed with prescribed amount of H2O and see how well it sticks. All right. And based off of that, you can infer binding energies. And this is a plot of the temperatures at which water H2O desorbs. You can see under laboratory time scales, ice desorbs about 150 and water about 220 on different materials. And they derived activation energies, and And the stability of this material is, well, it's really not that stable. So what would happen is that in the middle slide, you can see water coming in, and if the surface warms up, or unless the surface is truly cold, the water will be unstable and it will migrate both into and out of the surface. And you could potentially, if you have a subsurface reservoir, have a water cycle, perhaps water being lost from the surface, reabsorbed somewhere else, migrate in, migrate around, and have a dynamic kind of equilibrium. On what time scale does this occur? Well, based off of estimated activation energies or desorption energies, I think about 0.55 EV, it doesn't take long at all, and Michael's going to get in this too, for water to desorb from a single grain. The plot you see up there is water molecule actually migrating around the grain. That's easier for water to migrate around the grain because you don't have to actually fully break the bond. You only have to weaken it. You can migrate around. So that is easy to do, so it happens more rapidly, but you don't move quite as far. You can move further with a single hop, but then you have to break the entire bond. So what happens? You migrate from grain to grain via along one grain, then through grain down, and so forth. You hop from grain to grain. And through multicolor modeling, we attempted to, Greg usually attempted to model in the black line, absorption from grain to grain. So how long it takes at different temperatures for water to drop off of one grain and go to another. And then the blue line is, correction, the black one is the migration around a grain and then between grains. And the blue one is a hopping from grain to grain. And you can see that at colder temperatures, I have to get my head wrapped around this one. Yeah, the black one happens a little bit faster. But in any case, it all happens, it has to be very, very cold for the water to be stable on individual grains. Now, what if you have many grains above you? So we modeled migration through 100 microns of 1 micron grain. It takes something like that. Yeah. We'll wait till they finish eating lunch. Hello.
Airlines mute, please.
All right. And it takes up to, I think, about 200 Kelvin. It takes about a lunar day to desorb for a water molecule potentially to move 100 microns. We chose this because that's probably the optical depth of 3 micron light. And we're trying to understand just how far, and we explain a diurnal variation in the water band depth on the moon. As far we could through the migration of H2O at these temperatures. Okay, extrapolating in billions of years is difficult, but possible. Regardless, though, what we have here is a cartoon, and don't take too much look at it too much. But if you go back a little bit, you can see at 125 Kelvin, which is almost normal stability will be quite long, especially for migrating water molecules. So simply mapping the distribution of average 125 Kelvin temperatures from finer data, you can see there's a lot of areas outside the PSRs themselves that could potentially be cold enough to retain adsorbed H2O without actually, without needing the coldness of that required to retain water ice, which would be there in white, which would be the deepness of the PSRs. And this adsorbed water could potentially form something like a disseminated deposit of water in the near surface, and in the plot there show what a terrestrial gold deposit looks like, which is at actually a lower concentration than what we estimate the water abundance to be on the moon of 1,000 ppm. Okay. In any case, so let's go and look at the physical state of this water, because it's brought up that OH, water that hits the surface forms OH, and that's absolutely true.
The conference is now in talk mode.
What does that mean?
I don't know.
I'm allowed to talk or not? All right, I hear people giggling, so I guess somebody hears me. All right.
I can still hear you.
We can hear you, yeah.
Good, fantastic. So we have two plots, one out of Carly Peters' science paper and the one there. And what I drew for the red line is the same in both of them. It's about 2.8 microns is where absorption due to OH commonly occurs. And you see that centers up nicely with the okay. I infer, because this is illuminated terrain, that most likely is OH, and that is consistent with Sunshine's work from the epoxy. But you have to be careful about ascribing the physical state of water based off the shape of the absorption band. These are some transmission spectra taken by some collaborators with Darby Dyers, showing that the absorption band position on the left is transmission spectra. On the right are reflection spectra. I took the reflection spectra in ultra-high vacuum so that should be free of any surface water and only see internal OH or surface OH. And the left shows transmission spectra that only see internal OH of lunar analog glasses that were made in a very low water environment. You can see that even though there is some water in it, I mean, there's still residual water in it, and the band positions shift depending on composition. So you have to be very careful when you say there is water or isn't water based off the shape of the band. However, OH tends to be pretty short. I have 2 minutes. And also the strength of the band changes with composition. All right, so let's move on to carbon dioxide. We see very similar things on icy satellites. And in fact, this is what got me interested to begin with, the possibility of H2O absorbing onto the soils in the moon. Unbeknownst to me, people have been looking at this for decades. But regardless, for Callisto, sorry, I should go back. This is a map of the strength of the 4.25 micron CO2 band. And it goes from 0 to 40% with continuum representative. Because the band is so strong, the nu 3 fundamental is so strong, that's only probably less than 1,000 molecules in optical depth of the surface. But nonetheless, it seems to be associated with recent impacts, and either delivery or maybe excavation from the subsurface seems to be the cause of it. Perhaps even radiogenic production from the Jovian magnetic field. We aren't really sure. But in any case, the band position is consistent with not CO2 ice, but perhaps some trapped molecule. And in experiments we conducted, we found a similar relationship to water ice in that the composition of the adsorbate strongly affects the position of the 4.25 micron absorption band associated with CO2. That's the only point of this plot right here. That one, it is dependent on composition, but of course, adsorbed molecules are, in this case, distinguishable from the water ice spectrum itself. And the case is the same for water ice. If I just said water ice, I meant CO2. But anyways, both of them are distinguishable from the ices. Another example of how the composition affects the position of the band. In this case, a smaller, higher charged cation actually, when it's bound to a CO2, will shorten the bond length and increase the energy of the CO2 vibration, shortening its wavelength position. Okay. In the laboratory recently taken, we've desiccated some meteorite samples. We're interested if it is possible that carbonaceous chondritic asteroids or that material accumulated on the moon could potentially adsorb CO2 at temperatures greater than at which the ice would be stable. And on some CM materials it looks promising, on others it does not. Applied 2.85 microns for reference for these two different meteorites. And these two meteorites do adsorb CO2. Only one of them, though, appears to have it stable at 150 Kelvin. These experiments were done at 150 Kelvin, which is well above the sublimation point of CO2. And based off the shape of the absorption band, it is not CO2 ice either. We see that from the Bell's meteorite appears to stably hold on to CO2. Quite interesting compared to Mercer's, and both of them are CM chondrites, or CM2s. In fact, not all CMs are created equally, and we are currently investigating why some of them appear to adsorb CO2 more strongly. In fact, we find that very few do. But still, this may give us some insights into once we understand what process responsible for that may give us some insights into what is absorbing the CO2 on the surface of Callisto, and et cetera. So anyway, in conclusion, since we're about out of time, there may be warm reservoirs of volatiles in the solar system, which is the point of our work to understand if volatiles can be thermally stable by absorbing onto these refractory materials, whether it's a CM conductive materials for CO2 or silicates for H2O. And that IR spectra can distinguish adsorbed states from ices, although you must be careful in inferring the in investigating the OH band itself, because its strength and position are very dependent on composition. And I think I'll stop right there. Thanks, guys.
Wonderful. Thanks so much.
Thank you.
Do we have any questions? I see one person typing. Okay, now we have two people typing.
Great.
In the meantime, Dave Page, please get ready for your talk.
Actually, I've got a question while we're waiting for the typing to finish. When you were showing an early slide, you had a black curve, a red curve, and a blue curve. And the red curve I understood easily, but the black and red, was there maybe something, black and blue, was there something maybe mislabeled there? If you could, I don't know if it's easy to go back to, but it said...
Was that the filter time of water from a grain?
It was, yeah.
Migration versus hopping.
It was migration versus hopping was the issue. It was migration and it said grain to grain, and it was hopping and it said grain to grain. And
right. That's exactly what I'm saying. So you go from grain to grain by migrating along a single grain, and then going from point to point, assuming the grains are in just a single point contact. And that one can model that, the speed that occurs, or it can migrate from grain to grain by just hopping from one to the other. The hopping takes more energy, but it occurs, it's a much more direct route.
Okay, so then if I'm remembering right, the black line was on a grain, just on a single grain, and the blue line was hopping from one grain to another grain?
The one that happened, but the two lines that happened more quickly than the third line, one of the lines just took a lot longer. That was migration through the diffusion from along a grain, so that appears to be faster than hopping from grain to grain. That one is diffusing through 100 microns of the surface. So the red line is diffusing through 100 microns
right.
of the surface. Okay. All right.
Okay.
And the black and the blue are different ways of hopping from grain to grain, but not. And the assumption is that each grain is 1 micron in diameter.
Okay, great. And George is saying, can we please remind everyone who called in to please mute their speaker? Yes, thank you. That's a very important thing to remember. Mute their, their mic. And Micah has a question. Are you able to distinguish the chemical state of the OH, the hydrogen bonded versus the defect bond?
Well, so the OH that we see is internal or can be absorbed onto the surface. So it is all, let's say, chemically interacting with it. It's no longer hydrogen bound per se. It's not water that is hydrogen bound to the surface. So there is a compositional dependency in the position of the OH band. So we can, and also we can distinguish OH from H2O. Okay. Now what we are not, and I have not looked at in great detail, and I don't, but my feeling that this isn't possible is that large amounts of physisorbed H2O, okay, which is typical when you're not under authorized vacuum where you haven't baked something off. All those H2Os generally have an absorption band at 2.95 microns because you're dominated by water-water interaction there. Okay. Now, can we identify, and what we are not sure that we can do is, can we identify the presence of a monolayer of H2O? Does that look different from a submonolayer of OH, which is what we know will be stuck on it, and that is what we know exists there after we we evacuate something down to 10 to minus 8 torrs and we bake it out at, at several hundred Celsius, there's only going to be OH left there. So I'm going to ask, let's see. So we can tell the difference between OH and different materials and between OH and H2O, but I'm not sure if we actually have been able to make successfully a monolayer of H2O and have spectrally characterized it. In general, you can get many layers of H2O under ambient conditions, and that tends to look like bulk water at 2.95 microns.